I'm a theoretical particle physicist, and yes, I think I can convince you that my research is fascinating. In fact, you already know some of my favorite particles, electrons, for example, or photons. They're the particles of light. Studying them means we can understand why they bounce off of molecules in the atmosphere, making us see a blue sky. During the last decades, many other fascinating particles have been discovered, and my job as a theorist is to understand and precisely calculate what happens when two of these particles crash into each other. So what do I mean by precisely? Imagine you're standing in front of a wallpaper, but you're really far away, so all you can see is that it is blue. If you move closer towards it, at some point you realize that actually it's made up of this beautiful mosaic. It is still a blue wallpaper, but now you have a much more precise understanding of it. In particle physics, we try to do the same thing, but with every step we take forwards, our calculation becomes much more complicated. You see, with the traditional calculation techniques, we're not able to see the mosaic right now, even though experiments are starting to see it. In order to check whether our understanding of the world of particles is the same that we actually observe in experiments, we need to improve our calculation techniques. So, let's move towards the wallpaper together. Let me ask you a question. Do you think that for calculating the path of the planets around the sun, you need to take into account our moon? Well, you don't. It is so much lighter than all of the other objects in that system that it really does not have a noticeable effect on the outcome. In my calculations, I try to do the same thing. If one of my particles is a lot lighter than the others, I just pretend that it is massless. I'm making a small mistake there. But that's not a problem, because I know how to systematically decrease the impact of this mistake. If it's that easy, why is not everyone doing this? Well, you see, in particle physics, we work in 4 dimensions. 3 spatial ones, plus time. But time is not exactly the same as the spatial dimensions. And this mathematically has a consequence that in your calculation, you do not exactly know what is large and what is small. My group has developed a method that allows us to treat the time component of the calculation in a different way, leaving us with an expression that we can simplify, because we do know what is large and what is sufficiently small to neglect it. We've already seen that this works for some specific processes, and I'm working on developing a generalized method so that we can calculate any process of particle physics with higher precision, which would lead us to be able to see not just one stone, but the whole mosaic.